So this is part one of our video series dealing with divisibility rules, prime and composite, and prime factorization. So this is the beginning of exam 2 module, and this will be in multiple parts. So this will be part 1. So what we're going to look at is different divisibility rules for certain numbers. And then we'll find how we look at how we find the factors of numbers, determine if something is prime or composite, and then look at how we can find the prime factorization of a composite number. So, difference between a multiple and a factor. When we think about this, multiples is a product of a number and an integer. Okay, so when we think about multiples of 3. It's like we're skip counting, okay? 3, 6, 9, 12, 15. 6 is a multiple of 3. 9 is a multiple of 3. 12 is a multiple of 3. 15 is a multiple of 3. You can also look at how the multiplication is involved when we're talking about multiples, okay? Multiples are what we get after we multiply the number by an integer, okay? So what's a multiple of 5? Well, we would say 15. Well, how did we get that? Well, we multiplied it by 3. So we would say 15 is a multiple of 5. We wouldn't say 5 is a multiple of 15. We would say 5 is a factor of 15. 3 is a factor of 15. So factors are what we can multiply to get the number. So 5 and 3, we multiply those together to get 15. So 5 and 3 are what we call factors. When we talk about divisibility, 6 is divisible by 2. Okay? Why? Because 6 is a multiple of 2. We see that 6 is equal to 3 times 2. So since 6 is a multiple of 2, we know that 2 will divide 6. 6 is a multiple of 3. We know that 3 will divide 6. 100 we know is divisible by 25. We know that because 25 times 4 gives us 100. So when we test for divisibility, so when I say give me numbers that are divisible by 2, you would give me numbers like 4 and 28 and 36 and 102. When you give me all these numbers, what we're noticing is that numbers that you give me that have a even number in the ones place, we know is going to be divisible by 2. So we know 2 is divisible by 2. We know 4, we know 6, and 8. And then let's look at, now we're getting into the 2 digits. So we look at the number 10. Well, 10 has a 0 in the ones place, but we also know that 2 times 5 is 10, so we know 2 will divide 10. I can repeat myself, and let's look at 22, 44, we'll say 56, and we'll say 68, and we'll say 70. Look at all these numbers. We know we can divide these by 2, but look at the ones digit, 2, 4, 6, 8, and 0. So the rule for dividing by 2 is if the ones digit has any of these numbers, we know it's divisible by 2, and also if we know it's an even number. How do we know if something's divisible by 3? Well, the rule of that is you start looking at numbers that are divisible by 3. So 3 times 2, we know is 6. Well, we know 3 will divide 6. 3 times 3 is 9, so we know 3 will divide 9. And 15, we know 3 will divide 15. and 21. We know 3 will divide 21. So we start looking at all these. We know 33 will divide by 3. So we look at this and we think, well, a rule for divisibility by 3 is the number is divisible by 3 only if the sum of the digits is divisible by 3. So take the number 15. We know is divisible by 3, but what is 1 plus 5? Well, 1 plus 5 is 6. Is 6 divisible by 3? That's your question. And you would say yes. Okay. Look at another one. How about 33? Well, 33, take the digits. 3 plus 3, we get 6. Your question is 6 divisible by 3? Yes. Well, then 3 will divide 33. Let's think of, how about 60? Well, 6 plus 0 is 6, and 3 and 6 is divisible by 3. So when you're looking at your numbers like 99, well, 9 plus 9 is 18. Is 18 divisible by 3? Yes. So we know that 3 would divide it. So we're looking at if the sum of the digits is divisible by 3. What do we know if it's divisible by 6 or not? Okay, so you think about your numbers that are divisible by 6. And so in class, I'll ask for some examples, but the things that we know are divisible by 6, and we'll look at some patterns. But what we know here is if a number is divisible by 6, we can look at the ones digit. And if we see 0, 2, 4, 6, or 8, we know that it's going to be divisible by 6. For instance, 12 has a 2 in the ones digit. We know that 6 will divide 12. We know that 24, we know 6 will divide 24. 66, we know 6 will divide 66. So look at you look at the ones column, and we see that 6 will divide it. We can also look at the sum of the digits. If the sum of the digits is divisible by 3. Well, we know that 72 is divisible by 6. But if you look at 72, we think, well, 7 plus 2 is 9. Is 9 divisible by 3? Yes. Does 72 end in 0, 2, 4, 6, or 8? Yes. So what we're saying is if, and it's twofold here, if the ones digit ends in 0, 2, 4, 6, or 8, which means it's divisible by 2, and has a sum divisible by 3. So what we're looking at is, can it be divisible by 2? Can it be divisible by 3? If it can, then we know the number will be divisible by 6. With 9s, wanting to know if it's divisible by 9s, we're looking just like 3s. We're going to look at the sum of the digits. Okay, so we know that 99 is divisible by 9, but look at 9 plus 9. That's 18. Will 9 divide 18? Yes. So we know 9 will divide 99. Well, we can look at 153. Well, 1 plus 5 plus 3, we get 6 plus 3, we get 9. Will 9 divide 9? Yes. So we're looking at the sum of the digits, and if the result of the sum of the digits, like right here, 18 and 1 or 9 after adding those digits, if we know that 9 will divide that result, then we know that number is divisible by 9. Then we can look at 5s. Well, the divisibility rule for 5s, if the ones digit is a 0 or 5, so if we think of 50, well, we know 5 will divide 50, but we know 5 will also divide 55. We know that 5 will divide 100, and we also know that 5 will also divide 555. So you're just looking at the ones digit here, and if you see a 0 or a 5, you know that 5 will divide it. And the same idea as with 10 is if the number is divisible by 10, only if the ones digit is 10. So if you think about that, well, we know 10 will divide 10, but not 15. So 10 will not divide 15 a whole amount of times, but what about 20? 10 will divide 20. 10 will not divide 25 evenly. 10 will divide 30 and 40 and 50 and so forth. So we're looking at the ones digit, and if that ones digit has a 0, then we know it's divisible by 10. And then you've got some practice with divisibility rules. All right, let's look at factors of a number. So again, if we have the product of A times B, and so A times B would be factors of whatever that result would be. So a number C A multiplied by B, these would be factors to create C, which we would say is a multiple of A and B. Now, let's think of factors of the following numbers. So if we talk about 5, then we're thinking about what numbers multiply to give us 5. Well, that would be 1 and 5. What about 18? Think about the numbers that multiply to give you 18. Well, that would be 1 and 18. That would be 2 and 9. That would be 3 and 6. And then we don't have any more. So those would be all the factors. I'll put a semicolon in between those. So 1 and 18, or I may just separate it with vertical bars there. Pairs, 1, 18, 2, 9, 3, 6. 23 would only be 1 and 23. If you look at 28, well, you're thinking 1 and 28 are a factor pair. 2 and 14 are factor pairs. And 4 and 7. So it has multiple factors. 32, we know that 1 and 32 are factor pairs. We know 2 and 16. We know 4 and 8 are factor pairs. And then look at 100. We know that it's 1 and 100. We know it's 2 and 50. We know 4 and 25. We know 5 and 20. We know 10 and 10 would result in that. And so then we start to repeat with our factors. So this is just, if you're looking for how to find factors, then you're listing. This is a way of listing to find them. When we talk about prime numbers and composite numbers, when we go back to this list here, we noticed that when we looked at 5 and we looked at 23, notice they only had 2 factors, 1 and 5 and 1 and 23. So when we talk about prime numbers is a natural number that has exactly 2 different factors, but it's only 1 in itself. That's a prime number. And when we looked at the number 5, it was only 1 and 5. 23 was only 1 and 23. So those would be considered prime numbers. When we're dealing with the composite, we're saying that it's other than 1. So, for instance, 24. Notice we had 1 and 24. We had 2 and 12. We have 3 and 8. We have 4 and 6. You already have more than 2, so that's why it would be a composite number. You can look at all of these. You can look at these numbers and determine which are prime. And what we'll see is 1 is neither prime nor composite, so it's kind of a special one. It's not prime and it's not composite. If you look at 2, well, 2 is only 1 in itself, so 1 and 2. 7 is prime because it's just 1 and 7. 11 is prime, it's just 1 and 11. 43, 1 and 43. 59, 1 and 59. 1 and 49. But if you look at the rest of them, you're going to see, well, 8 has multiple factors. 1, 8, 2, 4. 9 would be 1, 9, and 3. 18 would be 1, 18, 2, 9, 3, 6. 27, notice that 7 plus 2 is 9, so we know that 9 will divide it. And 3 will divide it as well. So we know we've got 1 and 27 and 3 and 9. So that's a way to look at your primes. You can also Google this if you wanted to. You could do a list of prime numbers and you would see everything in yellow would represent your prime numbers. So I would suggest that you look at some of your practice links if you need to in order to practice the difference in prime and composites. Finally, we're going to look at how we can find the prime factorization of a composite number. Notice we're not doing a prime factorization of a prime number because the prime factorization is you're trying to get your product of primes. And the only way to do that is that you take a composite number to get it down to primes. If it's not composite, it is prime. So that's why we just do a prime factorization of composites. So let's look at 39. Well, we know that that's going to be 3 and 13. And we know that 3 is prime, and we know that 13 is prime. So this would be your final result as a product of primes. Take 220. Well, I notice it ends in 0. So we could always start with what things that we notice. I know it's going to be 10, and I know it's going to be 22. So 22 times 10 gives me 220. Well, I need to take 10 and simplify it and find the factors of 10 that I'd like to get to prime numbers, and 2 and 5 are both prime. 22 would be 2 and 11. So 2, 5, and 11, and notice they're all on 2, 5, and 11. So we know that those are prime numbers. Take 72. I could say 8 and 9. Maybe 8 and 9 came to your mind as factors. Well, 8 is not prime and 9 is not prime. So what we have to do is continue to break these down into their primes. So 8 would be 2 times 4. 2 is prime, but 4 needs to be factored again, and we see that it's 2 times 2 times 2 is the same as 8, and then 3 times 3 would be 9. So notice what we have here. 3 2's and 2 3's multiplied together. So when we do our prime factorization, I want you to use exponents to represent that. Here we would have 2 to the second times 5 times 11. So 220 is represented by this. And 39 would just be 3 times 13. So what about 75? So if we had the number 75 and we're finding the prime factorization, well, that would be 3/4, right? 3 25-cent pieces if we're talking money. So 3 times 25. Well, we know 3 is prime, but 25 is not. It's 5 times 5. Now we've made it to our product of primes. So we would write this as 3 multiplied by 5 to the second power. Another one, let's look at 1200. Well, with 1200, I see 2 zeros here, so I know 100 is a factor, and I would have 12. So 12 is still composite, so I'm going to factor it to 3 times 4. You could have used 2 times 6. Doesn't matter what factors you choose, you're still going to break down the number in factors. So 3 is prime, 4 is not. It's 2 times 2. Now it's a product of primes. 100 is going to be 10 times 10, 2 times 5, 2 times 5. We made it to our product of primes. Now, let's go from least to greatest. I see 1, 2, 3, 4 2s, so 2 to the 4th times 1, 3 multiplied by 5 to the second. Here is your product of primes written with exponents. And so the next page, you can kind of look and see how you would break these down. So here's your prime factorization of those numbers, but then this is the format that I want is for you to use exponents, because that's what exponents represent, right? When you're thinking about order of operations, exponents represents repeated multiplication. That's why exponents is second in the list in your order of operations. Exponents comes before multiplication because exponents represents repeated multiplication. Why does multiplication become before addition when we're looking at order of operation? Because multiplication is repeated addition. So if you need some practice with prime factorization, I would encourage you to look at the links there. So this will conclude part 1 of our video series with divisibility rules, prime and composite, and prime factorization.